Welcome to the video lecture series for Texas A&M University Course Math 152. Today we will look at Section 8.2, Trigonometric Integrals. You can find the accompanying handouts at bit.ly/RaeleneMath152. Let's begin. We will consider looking at the following derivatives to warm up on the trig derivative antiderivative pairs. The derivative of sine x is equal to cosine of x. And if we wanted to derive this one, we could go back to the basic limit definition of a derivative, which says that f prime of x is equal to the limit as delta x, or h, approaches 0 of f of x plus h minus f of x all over h. From here, we can apply the same limit definition of the derivative to get the derivative of cosine of x, which is negative sine x. The derivative of secant x may not be as familiar, but we wouldn't necessarily have to go back to the first principles or limit definition of the derivative. We can instead use some of the derivative rules and recognize that secant x is the reciprocal of cosine x. So we could write this as the derivative of 1 over cosine x and use the quotient rule, or cosine x to the exponent of negative 1 and use the chain rule. So I get negative 1 times cosine x to the exponent of negative 2 multiplied by negative sine x. And from here we see that the derivative is going to be positive sine x over cosine squared x, which is sine x over cosine x, or tangent x, times 1 over cosine x, which is secant x. So you can apply the basic derivative rules if you forget these basic derivatives. You can apply quotient rule, chain rule, product rule, etc., or the limit definition of the derivative. The cofunction of secant x is cosecant x, and its derivative is negative cosecant x cotangent x. Again, if you're not sure, you can write cosecant x as the reciprocal of sine x and apply the same technique as in part B. The derivative of tangent x is secant squared x, and if you don't remember, you can rederive this by calling tangent x sine x over cosine x and using the quotient rule for derivatives. Similarly, you could apply the quotient rule for cosine x over sine x to get the derivative of cotangent x, which is negative cosecant squared x. And the reason I have organized them in this way is that the three functions at the top all have derivatives that do not involve a negative sign, and the three functions in the bottom are all co-something. Cosine, cosecant, cotangent, and their derivatives all involve a negative. In number 2, we want to determine the integral of sine x cosine x dx by two different methods. So method 1, we may actually start off by seeing that we have a product here, and we might want to use the product rule, or rather the integration by parts technique for a product. And so if we start off like this, we could set u equal to perhaps sine x, which means that dv is equal to cos x dx. And therefore du is equal to cosine x dx, and v is equal to sine x. There seems to be a lot of symmetry going on here. Let's see how that plays out once we do the integration by parts technique. So the integral of sine x cosine x dx will expand by the quotient, or rather the integration by parts technique, as u times v, which is sine squared, minus the integral of v du, which is going to be sine x cosine x dx. And in this case, while it looks like maybe we haven't made any progress, we notice that this integral is the same as this integral, so if we take it to the other side, we get 2 times the integral of sine x cosine x dx is equal to sine squared of x, and therefore we can say that the integral of sine x dx, cosine x dx is 1/2 sine squared of x plus a constant. Well, in fact, maybe there's another approach here because we were getting some of the same terms back and forth. Maybe we didn't need to recognize this as a product, and we could have used the chain rule, rather the method of substitution for composition. So as a second method, if we have the integral of sine x cosine x dx, I'll write it over here. We can recognize that the derivative of one of the functions or factors is already here, and so we could use method of substitution for either sine x or cosine x to be the new variable. I know that sine x's derivative is cosine x, meanwhile cosine x's derivative is negative sine x. But since I don't have the negative, I'm going to choose t equal to sine x. And therefore dt is equal to cosine x dx. So this integral transforms into the integral of t dt, which seems a lot simpler than the method of substitution. And here we get t squared over 2 plus c, which is sine squared x over 2 plus a constant. Well, in fact, there's even a third technique that we can approach. And it gets a little bit simpler still because we can recognize that we have trig identities that we can use to rearrange. And in method 3, using trig identities, we notice that sine of 2 times x is equal to 2 sine x cosine x. And therefore, sine x cosine x from the integral can be replaced as 1/2 of sine 2x. So our integral sine x cosine x dx can be rewritten as 1/2 integral of sine of 2x dx, which gives us 1/2 times the antiderivative of sine of 2x, which is going to be negative cosine of 2x, divided by 2, and then plus c, which gives us negative 1/4 cosine of 2x plus c. And at this point we may say, but these don't look the same. So we have to recall our trig identities that relate these things. And we can expand cosine of 2x using cosine of x plus x as cosine squared x minus sine squared x. Or furthermore, let me put this on a new page. And so if we expand this further, or rearrange this further using the Pythagorean identities, we can say that sine squared x is 1 minus cos squared x. Changing the sign gives us 2 cosine squared x minus 1. Or similarly, substituting cosine squared x, we can get 1 minus 2 sine squared x. And as a result, we can see that sine squared x is equal to 1 minus cosine of 2x divided by 2. In other words, negative 1/2 cosine of 2x plus 1/2. And so from method 2 and 3, we saw the same result of sine squared x over 2 plus c. So sine squared x over 2 plus a constant is equal to 1/2 of this result, which is going to be negative 1/4 cos of 2x plus 1/4. Well, we can see that we have different constants here, and that's why we have the same result from method 2 and 1 as we do in method 3. There's the negative 1/4 as opposed to the positive 1/2 for the sine squared x. So in fact, in that previous example, we had 3 techniques: integration by parts, method of substitution, and good old trigonometric identities that allow us to transform the integral directly to a basic integral. In number 3, let's determine the integral of tangent of x dx, and then we'll do part B. So the first thing we notice is that tangent of x is not someone's derivative. And so it may be practical, as we did for the derivatives, to express tangent of x in terms of the sinusoids, sine and cosine of x. Here we can recognize a substitution possibility, and I'm going to let t equal to either sine x or cosine x. Given that we want the derivative to multiply by dx, I'm going to choose t equal to cosine x. And therefore dt is equal to negative sine x dx. And we can transform this integral to negative dt equal to sine x dx. So we get negative the integral of dt over t. And this gives us negative the ln of the absolute value of t plus a constant, which is equal to negative ln of the absolute value of cosine of x plus a constant. And if I wanted to bring this -1 coefficient up as an exponent on the power of absolute value of cosine x, I could rewrite the result a little more simply as the ln of the absolute value of secant of x plus c. And let's just check our result. Let's take the derivative of the ln of the absolute value of secant of x plus c. So we notice that we have the ln of the absolute value of the secant of x. And so we have a three-level composition, f of g of h of x. And we have to apply the chain rule. So the derivative of ln is 1 over the stuff that was on the inside. Now the derivative of absolute value is the absolute value of the stuff divided by the stuff. So we get the absolute value of secant of x divided by secant of x. And now the derivative of secant of x is secant x tangent of x. And if you wanted to keep going, you'd say that the derivative of x is 1. So that's how you know when you finish the chain rule. Then the derivative of a constant is 0, and we can simplify this to give a result of tangent of x, which is good because that's the function that we started with. In part B, we want to integrate cosine squared x minus sine squared x with respect to x. Do keep brackets around the function, as we know that this is similar to saying f of x times dx, height times width of a rectangle, from the Riemann sum approximation. Neither of these is someone else's basic derivative, so these are not basic antiderivatives. But we do recognize a trigonometric identity here, namely that cosine squared x minus sine squared x is cosine of 2x. And since this is a basic antiderivative, we can simply integrate. If you want, you could have used a method of substitution for the inner function and let t equal to 2x, and therefore dt is equal to 2 dx, and therefore dx is equal to 1/2 of dt. But recognizing that we can scale out that factor, which would have come from the chain rule of multiplying by 2, we can reverse the chain rule in one step by dividing. And so we end up with sine of 2x over 2 plus c. Of course, there are other ways we could write sine of 2x. We could write it as 2 sine x cosine x multiplied by the 1/2. And so another equivalent name for this is sine x cosine x plus c. In number 4, we're asked to do some trigonometric proving, just to remind ourselves of the identities. Prove that sine squared theta is equal to 1 minus cos 2 theta over 2. We've actually already done this one, so I'll leave you to reproduce the details here and be very comfortable with that. Similarly, in proving cosine squared theta is equal to 1 minus sine 2 theta over 2, we require the same idea, which is to start off with cosine of 2 theta equals cosine of theta plus theta, which we can expand as cosine of the first times cosine of the second, minus sine of the first angle, sine of the second angle. And from here, I had started already at cosine squared theta minus sine squared theta a few slides earlier, and we can reproduce part A or part B from here. In part C, we want to prove that 1/2 tan squared x plus c1 is equal to 1/2 secant squared x plus c2. And it requires us to start from the Pythagorean identities. The easiest one to notice is that sine squared of x plus cosine squared of x is equal to 1. And so if we take this equation and divide it through by cosine squared x, we will have the terms of tangent and secant, which have cosine in the denominator. And so when we divide through by cosine squared x, we get tangent squared x plus 1 is equal to secant squared x. So from here, we can actually rearrange and get the results that we're interested in. We can say that 1/2 tangent squared x plus c1, if we start from the left side, I'm just going to make this clear, is something new. 1/2 tangent squared x plus 1 can be replaced, plus c1. We can replace the tangent squared x with secant squared x minus 1 plus c1, and we know that we're going to have 1/2 secant squared x, which is good, plus c1 minus 1/2, and we simply gather that expression up and give it a new name of c2. And so we end up getting the right-hand side, and we've proven the result. Part D is a different proof. This is called the product to, in this case, sum, but it could be a product to sum or product to difference identity. And on the pre-calc no cold or on the resources page under the pre-calc review materials, you will find all of the trig identities that you need to know, including the product to sum and product to different identities. In part D, for the proof, I'm going to start with the right side, which says 1/2 times sine of a minus b added to sine of a plus b. And I'm going to use my sine of a sum or sine of a difference expansions, which you can also find on the trig identity sheet, in which I had used in the part A and B expansion for cosine of theta plus theta. So we get 1/2 times sine of a difference expands as sine of the first, cosine of the second, same sign, plus or minus, cosine of the first, sine of the second. And then the sine of the sum of two angles expands as sine of the first, cos of the second, same sign in between the angles, which is a plus, cos of the first, sine of the second. And it doesn't take very much work to see what happens here. We get negative cosine A sine B plus cosine A sine B, and inside the brackets we have 2 sine A sine B, and the 2 and the 1/2 reduce, leaving us with sine A sine B, which is the left-hand side of this identity, and we're done. QED, quod erat demonstrandum, which means in Latin it was shown or demonstrated or proven. In number 5 then, we want to integrate the definite integral from 0 to pi of sine squared x dx. Again, sine squared x is not a basic antiderivative. It is not someone's direct basic derivative. And so what we want to do is consider an alternative way of expressing sine squared x. We could try method of substitution. We could try integration by parts. If we broke up the integral of sine squared x, or if we just broke up sine squared x, we could see it's sine x times sine x dx. But it's not as obvious as the version when we had multiplied by a cosine x, because we don't have the derivative of sine x involved here. So I don't recommend using either product rule or the integration by parts technique, but what we do know is that sine squared x, from our proof earlier, can be written as 1 minus cosine 2x all over 2. And this is not a change of variable, it's simply an identical or trig identity replacement. So we are going to say that the integral from 0 to pi of sine squared x dx is equal to the integral from 0 to pi of 1/2 minus 1/2 cos 2x dx. And now, without any method of substitution or integration by parts, we have two basic antiderivatives. And so we get 1/2 x minus 1/4 sine of 2x integrated from 0 to pi. So from here we get 1/2 pi minus 1/4 sine of 2 pi, subtract 0 minus 1/4 sine of 0, and both sine of 2 pi and sine of 0 are 0, and we are left with 1/2 of pi. Of course, you can check your result on a graphing calculator like TI Inspire and see how you got on. In number 6, we want to determine the integral of sine x cosine squared x dx. I'm going to encourage you to pause the video and think about this for a moment and try some different techniques. Don't be afraid to make a mistake. That's how you get better. Well, there are a couple of possibilities. We can express this as a product. So we can see that we've got sine of x times cosine squared of x dx. So maybe we want to use integration by parts. We could also rearrange the product so that we have sine x cosine x multiplied by cosine x dx. If that suggests a better reorganization. We could also see that we have a composition. And writing it in this form may make something seem a little bit more logical. So sometimes just a matter of rewriting this can help us to see different approaches that we might take. Furthermore, from pre-calculus, the trig identity, the Pythagorean identity for cosine squared x is 1 minus sine squared x. So perhaps one of these jogs an idea and gives an insight as to how we might proceed. It turns out that this approach, using the trig identity, is not going to be helpful because the entire integral will be in terms of sine, and there will be no derivative of cosine multiplied by the dx. So we won't go with this approach. Furthermore, we see that the two product rule possibilities, the first and the second one, well, they may work, but it would take a little bit of trying to find out what u and dv would have to be. We can see from our previous experience in 6.5 that if we have an inner function, it's a very good candidate for our substitution, which I'm going to use as t. And furthermore, we have the derivative showing up here. So I'm going to go with the method of substitution. We're going to let t equal to cosine of x, and dt equals negative sine x dx. And so we can proceed by calling this the integral of t squared times negative dt. So we get negative t cubed over 3 plus a constant, which is negative 1/3 cosine cubed x plus c. And of course, taking the derivative of this should produce sine x cosine squared x. Now we're ready to look at integrals of the form sine to the m of x times cosine to the n of x dx, where both m and n are whole numbers. So the first process or approach is if we notice that the n, the exponent on the cosine, is odd. If it is, then we can write it as 2 times an integer, or a whole number, k, plus 1. So what we're going to do is replace n with 2k plus 1, and then we're going to rewrite that, breaking apart the cosine factors. So we're going to have something to the k times something dx. We're leaving sine to the m of x the same, which means that inside the brackets we would have cosine to the 2k, which is cosine squared x all to the k, and then there's one cosine left over. The reason we're doing this is because we can see that cosine x dx is going to be the dt, which means that t would have to be sine of x. And then we can recognize that all of the rest of this can be expressed in terms of sine x, except for the dt part, by using the trig identity for cosine squared x as 1 minus sine squared x. And so it's a method of substitution with a slight breaking apart according to the trig identities and the Pythagorean identity for cosine squared x. If m is odd, then we have the odd exponent on the sine term. And we can break the m exponent up as 2k plus 1, and then we can break sine to the 2k plus 1 of x apart. Take a moment and see how you might do that using another trig identity, rearrangement, and substitution. Well, in this case, because we have an odd or leftover sine of x, we're going to put that in with the dx. And then that is what turns into the dt? Well, it could be plus or minus, as we've seen before. We can always work out the negative sign later on. So if we're going to have a sine x here, then it suggests that we would let t, the substituted variable, be cosine of x. And so what we're going to have inside here is sine squared of x all to the k, so we multiply the exponents, but then we still have a leftover sine x that we've put here, and the cosine to the n of x remains intact. However, since we're going to be doing a substitution for cosine, we want to substitute or replace sine squared of x using the Pythagorean identity, 1 minus cosine squared of x. Okay, let's take a look at an example of applying these approaches, which are really just combinations of previous approaches of trig identities and the method of substitution. Determine cosine cubed of x. Well, we've got an odd exponent on the cosine, so we really want to break free one of those cosine of x's and combine it with a dx. You don't need to memorize the previous table of approaches, but we can recognize that if this is going to be dt, then for our method of substitution, we really want t to equal sine of x. The problem is we don't have a sine of x, but we do if we use the trig identity for Pythagorean identity, that cosine squared x is 1 minus sine squared x. And from here, we can do the substitution that t is equal to sine x. So we get 1 minus t squared times dt, which is now a basic antiderivative. We get t minus t cubed over 3 plus a constant, and we back substitute to get sine x minus 1/3 sine cubed of x, and then plus c. Now, it's entirely possible that a different technique could have produced a different looking result, but as we've seen in some of the warm-up or first few slides, we've seen that different looking trig expressions plus a constant are actually identical because of different rearrangements with Pythagorean identities or the sum, expansion, or half angle, multiple angle identity formulas. In part B, we want to expand or integrate cosine squared x sine to the 5x dx. Well, we notice here that we have an odd sine x factor, so we are going to expand this by freeing or separating one of the sine x's and consider that it's really being joined by dx. So that suggests that we are going to have dt equal to sine x dx, which really suggests that we're letting t equal to cosine x or negative cosine x. Well, if we let t equal cosine x, then dt is negative sine x dx, or sine x dx is negative dt. So we just adjust for the negative sign later on. But this is a very good indication of how we are going to proceed. So if we want to express the t variable for cosine x, we have to do something with the sine to the 4x. Namely, we can recognize that this is sine squared x all to some exponent. And we know that 2 times 2 is 4, so we have an outer exponent of 2. And we still have to rewrite everything except for the differential part in terms of cosine. So we're going to use the trig identity, or the Pythagorean identity, that says sine squared of x is 1 minus cosine squared of x. And we have that quantity all squared. So now we're ready to do our substitution. And when we substitute, we get t squared times 1 minus t squared all squared times negative dt. And this is a basic antiderivative. We simply need to expand it, so we're going to get t squared times this quadratic expanded. So we're going to get 1 minus 2t squared plus t to the exponent 4, all multiplied by negative t squared. And so if we do that all in one step, I'm going to write my positive term first, so I'm going to get positive 2t to the 4 minus t squared and minus t to the 6 dt. And so we get 2t to the 5 over 5 minus t cubed over 3 minus t to the 7 over 7 plus c, which back substitutes or expresses in terms of cosine as 2/5 cosine to the 5x minus 1/3 cosine cubed x minus 1/7 cosine to the 7x plus a constant. And if we took this final blue function and took its derivative, we will get cosine squared x sine to the 5x. In number 8, we want to determine by the most efficient method the integral for sine to the 4 of x. And I'm going to leave you to try this one, part A and part B, by thinking about method of substitution, trig identities, and integration by parts. If you have to try 2 or 3 different methods before you conclude which one is the most efficient, that's perfectly fine. Now we're going to look at integrals of the form involving tangent of x and secant of x powers and their products. So we're going to say if m and n are whole numbers and n, the exponent on the secant x factor, is even, we can write n as 2 times k, where k is some other whole number. Really, I should say where m, n, and k are whole numbers, but at this point we hadn't talked about k. So what we can do is rewrite the secant of n as secant to the 2k, rather secant to the n as secant to the 2k. And so going through and filling in the blanks, we can say secant squared x is going to be secant squared x all to the exponent of k. However, there's another secant squared x over here. So what is really going on inside this bracket? Well, if we break it apart, we have secant squared x times something to give us secant to the 2k of x. And so we would have to subtract the exponents to find out the missing. So this is going to be to the 2k minus 2 of x. And then we have secant squared, we have this secant squared outside here, and we want to break this apart as secant squared inside and something in the box. So what we really have to do is factor out a 2, and we get 2 times k minus 1. And so the secant squared is the secant to the 2, and the k minus 1 goes in the box. Then we can recognize secant squared x is someone's basic derivative, and it is the derivative of tangent of x. So we will see that this quantity should be our differential dt, which means that we should let t be tangent of x. And so if that's the case, we want to express everything except for the differential part in terms of tangent. And so we are interested in a technique that involves tangent and secant because tangent and secant terms are found in a Pythagorean identity, as we saw earlier in the warm-up, by taking sine squared x plus cosine squared x equal to 1 and dividing through by cosine squared x. So we can say that secant squared x is equivalent to 1 plus tangent squared of x, and from here we will have all of that raised to the exponent of k minus 1. Now everything is expressed in terms of tangent except for the differential, which we will be calling dt. In the second possibility, if the exponent on tangent, if the m is odd, then we can write m as 2k plus 1. Take a moment and see if you can't fill in the blanks to see how you would proceed in an integral of this form. Well, the first thing we're going to do is recognize that we've kind of got an extra tangent, so we're going to want to make an even amount of tangents over here, meaning an even exponent, and one tangent over here. Well, that takes care of the plus 1 of the tangent of 2k plus 1 of x, because tangent to the 2k of x times tangent to the 1 of x is equal to tangent to the 2k plus 1 of x. And so this tangent has been grouped together with the differential, which means that we have tangent of 2k, tangent to the 2k of x left, and if the k is out here, that puts tangent squared of x inside the bracket. And that leaves us with secant to the n of x here, but there's another blank. So we're going to break up the secant of x and put one of them here because we recognize this as the derivative of a basic trig function. Tangent x secant x is the derivative of secant x. And so that's going to give us our substitution choice. And if secant x, one of the secant x's is over here, then from the secant to the n of x, we only have n minus 1 left here. And so when we rewrite that, we get secant to the n minus 1 of x, tangent x secant x. However, if we're going to substitute everything except the differential in terms of secant x, we need to replace tangent squared x with secant squared minus 1. Secant squared of x minus 1. And then we will be able to do a method of substitution from this rearrangement of the original integral. So in number 9a, let's determine the integral. In this exercise, we have an even exponent on both the tangent and on the secant. And so we know that we have the derivative of tangent is secant squared x. So we might want to have a differential of secant squared x dx, or the derivative of secant is secant x tangent x, and then with the differential dx. In this case, having only even exponents, we would have to take advantage also of the Pythagorean identity, tangent squared x plus 1 equal to secant squared x, which means that we cannot break apart one tangent x and one secant x, because then we would have odd exponents left, which would not allow us to take advantage of the Pythagorean identity. So what we're going to do is group a secant squared x dx together, which means we have secant squared x times secant squared x dx, and our choice for the differential is going to be dt is secant squared x dx, so that t is going to equal tangent of x. So now we want to express everything that's not in the differential in terms of tangent, which means we need to replace secant squared x using the Pythagorean identity. So we get tangent to the 6th of x multiplied by tangent squared of x plus 1 multiplied by secant squared x dx. And we're ready to use our substitution to get t to the exponent 6 times t squared plus 1 times dt. And the integration is quite straightforward from here after we do some expansion for the algebra. We end up getting 1/9 t to the 9, but you can directly back substitute in terms of tangent, plus 1/7 t to the 7, but t is tangent. And for an indefinite integral, don't forget plus c. Okay, I'm going to leave you to try part B on your own, keeping in mind that you really have two possibilities for dt. dt will either equal secant squared x dx, or dt will equal secant x tangent x dx. And we also have to take into consideration that the Pythagorean identities involve even exponents on tangent and secant. So with these facts, how can you proceed without memorizing a formula? Okay, moving on to number 10, we want to show that tangent x secant squared x dx is equal to both the first option and the second option. Well, we've seen in the warm-up, or the first few slides, that these two results are equal because the c1 and the c2 differ by a constant. So what we want to do is show that we can get the results in two different ways. So from tangent x secant squared x, we can see straight away by regrouping that secant squared x dx is the derivative of the tangent x with respect to x. So we are going to let t equal to tangent of x, dt is equal to secant squared x dx. There was no manipulation of the trig identities and the exponents required because these were already in basic function and derivative form. So we get the integral of t times dt is 1/2 t squared plus a constant. And so we can see, substituting with tangent of x, we get 1/2 tan squared x plus, let's call that constant 1. Now this is the first approach. We could have recognized, however, that this integral, let me call this a, or 1 rather, we could have recognized that the integral is split up in a different way, namely tangent x times secant x times secant x, which is not inspiring until we rearrange it as secant x times secant x tangent x. And again, this goes back to a basic idea that if you don't know how to work forwards in math, you won't be able to work backwards, and then you won't really have mastered the concept. So it is absolutely essential that you know your basic facts, limits, derivatives, integrals, cold, so that you can come up with the inspiration required to answer these questions. So now we could say, let t equal secant of x, and therefore dt is secant x tangent x times dx. And from this approach we get the integral of t dt is going to be 1/2 t squared plus c. Well, this is a different constant, c2, because t is now secant of x. So with a different rearrangement, we see a different inspiration and a different approach to the same problem. However, these two quantities must be the same, as we showed in one of the warm-up questions. In number 11, work out the integral of tan cubed of x dx. Well, to get a little bit of inspiration, I want to write it slightly differently, so I'm going to write it as tangent squared x times tangent of x dx. And then I'm going to think about it. I don't have a secant x here. I really could have said tan of x all cubed, and then I had an inner function of tangent of x, but I still have no derivative of tangent of x. So at this point, I might just write down the derivative of tangent of x, so I know what I need to get in the expression. I might also write down my trig identity to see if this is helpful. Hey, it turns out that the derivative of tangent of x is equal to tan squared x plus 1. Oh, I didn't really think of it that way before. From here, we could rewrite tan squared of x using the trig identity. That would introduce a secant squared, or secant x, that we need if we wanted to come up with the derivative of tangent of x. We need a secant squared x. So let's do that. Tangent squared x is equal to secant squared x minus 1 times tangent of x dx. So we can break this apart. Secant squared x times tangent x. Well, that's looking promising. And in fact, I'm going to break this apart into two integrals, minus the integral of tangent of x dx. So this one actually is now capable for substitution. We can see that if we let tangent of x be t, then dt is secant squared x dx. But unfortunately, tangent is not a basic antiderivative. However, we've seen this one in the warm-up, and we can rewrite tangent of x as sine of x over cosine of x. And then we have a substitution here, where we can let cosine of x be, let me make it z, and therefore dz will equal negative sine of x dx. So after a while, you will get more familiar or capable of doing method of substitution without writing down all the steps. We can see that this integral is going to be the integral of t dt, and then minus, except I'm going to absorb the minus with the negative dx here, and the sign, rather. I should have included the sign in that. So the negative, the sine x, and the dx is my dz. So I'm going to get plus the integral of dz or dz over z. And when we proceed, we get 1/2 t squared plus the ln of the absolute value of z plus a constant. And back substituting, we get 1/2 times my t was tangent of x, so 1/2 tangent squared x, plus the ln of the absolute value of cosine of x, plus a constant. And of course, if this is a function f of x, you should check that f prime of x does in fact work out to be tangent cubed of x. In the next example, we have secant cubed of x, and I'm going to leave you to try that one as an example. Number 12 asks to determine the integral of secant x dx. There are no exponents to play with. It's not possible to introduce the Pythagorean identity of tan squared x plus 1. And we know that if we want to let t equal to secant x, we have to have a tangent x as well as another secant x in the derivative. So this is actually not turning out to have anything to play with for rearrangement's sake. So it sounds like we're missing things that we need. And what we need to do in this case is introduce some of the missing terms by multiplying by 1. But we multiply by 1 in a creative form. And in this case, we are going to multiply by 1 in the form of a fraction, which is a sum of two trig functions, secant x plus tangent x over secant x plus tangent x. When we do that, we expand the numerator to get secant squared x, which is a positive thing because we know it is the derivative of tangent x. And then we also get secant x times tangent x, which is also a positive thing because it is the derivative of secant x. And those two derivatives are added together. So the numerator must be the derivative of tangent x plus secant x, or the denominator, secant x plus tangent x. So you might ask the question, how could I possibly have known to do this red step? Well, again, you can only get creative or find inspiration if you know the forwards so well that you can start to see the backwards. So you really need to know your basic derivative and antiderivative pairs, all of the no-code from pre-calculus and calculus 1, before we can get creative and do a step like the red one. So here we can see that we can let t equal the denominator of secant x plus tangent of x. dt then is going to equal secant x tangent x plus secant squared x, and that's all multiplied by dx. Or we can rearrange the terms and we can make the derivative secant squared x plus secant x tan x. Either way, the numerator is dt and the denominator is t. So we have the integral of dt over t, which is going to integrate as the ln of the absolute value of t plus a constant, and t was equal to secant x plus tangent x. So we're going to add this result to our library of basic integrals. So memorize this, or know cold, know this one very well. The integral of secant x dx is equal to the ln of the absolute value of secant x plus tangent x plus a constant. Well, I'm going to give you a chance to get creative on your own. Try something in part B to evaluate the integral of cosecant x dx. It involves something similar, but I'll let you figure out what it might need to be based on what the basic derivative and antiderivative pairs are. So we'll leave you to try this one as an exercise. In the last set of trigonometric integrals that we will study in this section, if the integral is of the form of a product of sine of an angle times cosine of an angle, or sine times sine, or cosine times cosine, we are going to need to take advantage of the product, which is what we have inside the integral, to sum or difference, which is what we're going to do over here. We're going to turn a product into a sum or a difference of sines or cosines of sums and differences of angles. So we've proven the first product to sum identity in the warm-up. I'll leave it to you as an exercise to prove the second and the third version. So if we have a product of sine and cosine, we're going to use the first trigonometric identity, product to sum or difference. So we simply recognize that sine of 4x cosine of 5x can be rewritten as 1/2. It'll be the sine of the difference of the two angles, which is negative x, plus the sine of the sum of the two angles, which is 9x. So here we could say 4x minus 5x is negative x, and 4x plus 5x is 9x. And so therefore we get that the integral sine of 4x cosine of 5x dx can be rewritten, no transformation, rather no method of substitution yet, just a simple identical rearrangement using trig identities. The left side is identical to the right side. And we can also use the negative angle identity, or the symmetry of the sine function, to say that sine of negative x is the same as sine of x. Is the same as negative sine of x. We cannot, however, take the 9 in front. It doesn't work that way. We know this because we know that sine of 2x does not equal 2 sine of x. Rather, sine of 2x is equal to 2 sine x times cosine x. So it's not a matter of this coming out in front. That doesn't work. And from here, we have basic integrals, so we simply integrate to get the antiderivative of negative sine x is cosine x, and the antiderivative of sine of 9x is negative cosine of 9x divided by 9, and you can either put plus c inside the square bracket or close it and a plus c at the end. And we can just rewrite it without brackets. 1/2 cosine of x minus 1/18 cosine of 9x plus c. A word about brackets here. Technically, if we want the angle to be 9x, it needs to be in brackets, but we have kind of dropped that convention. We don't expect that cosine of 9x to be cosine of 9 multiplied by x. It's very unusual to see this, so even though this is more technically correct to say that cosine 9x means take the cosine of 9 first and then multiply by x, we generally think that cosine of 9x means cosine of 9 times x. Okay, this concludes section 8.2, trig integrals. Please ensure that you have completed the handout and prepared a list of clarifying questions about the lecture. And that's all for now.